you very much. Thank you for the introduction. Yes, I'm Amy Stidworthy from CERC. Yes, thank you to AQE for the invitation to present today. I'm hoping that this talk follows on quite nicely from earlier talks this morning from Pete and from Rod Jones about measurement uncertainty and low-cost measurements. So, since the beginning of the COVID-19 lockdown in March 2020, we at CERC, we've been trying to quantify the impact of lockdowns on air quality, and specifically on air quality in London. So I'm sure we could all see the effects of the lockdown at that time. So usually busy streets, usually almost completely deserted, like this photo of Regent Street, which is usually one of London's busiest shopping streets. And of course, there was much in the media about the air in our cities feeling cleaner at that time. So we've investigated what the real changes have been in terms of concentrations, but we've also used inversion techniques to try to estimate the impact on road traffic emissions. So next slide, please. So I'll start by explaining the motivation for this work, and then I'll remind you what the restrictions have been in London and what we know from the government about changes in transport activity. I'll then show you what we've found looking at air quality measurements, and then I'll move on to talk about the inversion techniques that we've used. I'll explain how our inversion scheme works, how we've applied it in London, and then I will show you the results and then look at next steps for this work. Next slide, please. So I'm sure we're all aware that huge changes have occurred in transport patterns since March 2020. And these changes carry the potential to cause massive changes in road traffic emissions compared with the established emissions inventories that air quality modelers such as ourselves are used to using. No one could have predicted these changes. And it's vital that we try to understand the effect of these changes, some of which may be with us to stay, for example, due to increased home working. Now, emissions inventories take time to collate, but we need an estimate of the changes on much shorter timescales for many reasons, for example, in air quality forecasting. And also, of course, this is an exciting and valuable chance to analyse and understand the effects on emissions and air quality of a massive step change in transport activity. Next slide, please. So to start with, let's refresh our memories about how the restrictions evolved in London in 2020 and through into 2021. So the first restriction in 2020 came in mid-March. From 17th of March, we were all asked to socially distance from others and avoid unnecessary travel. And then a week later, the first full lockdown, Lockdown 1, came into force on the 24th of March. We were only allowed to leave our homes for limited reasons. Schools were closed, except for the children of key workers. And these restrictions stayed in place until the 10th of May, when they were eased slightly, and we were allowed outside for unlimited exercise. And then a month later, restrictions were eased further, and all shops were allowed to open, but restrictions on social gatherings remained. And for 4 months, these lighter restrictions remained in place. But on the 17th of October 2020, London was placed into Tier 2 measures, which meant different households were not allowed to mix indoors. And then, on the 5th of November, we were placed back in Lockdown 2, where again we were all asked to stay at home wherever possible, but schools remained open this time. That lockdown ended on the 6th of December, but then on the 6th of January, England entered its third full lockdown, with schools again closed for most children. Schools opened again on the 8th of March 2021, and restrictions then gradually eased through into the summer of 2021. The graph shows government data on the use of different transport modes up to the end of September 2021. The data is for England, Scotland and Wales, apart from the Transport for London bus data, which is London specific. The changes for cars, LGVs and HGVs are compared with the equivalent day in the first week of February 2020. The change for the TfL buses is compared with the equivalent day in 2019. The large blips are bank holidays. The smaller blips are weekday weekend differences. The missing data for buses from April to June is because TfL introduced entry by the middle door to protect bus drivers, and no payment was required because the card reader is at the front of the bus near the driver. No payment means no data on bus use. All modes show some reductions in advance of the March lockdown, a dramatic step change on the 24th of March, down to very low levels, and then slowly increasing back up to near normal levels for HGVs and LGVs by mid-July 2020, but car use isn't back to pre-pandemic levels until June 2021. Car use drops to less than 40% of pre-lockdown levels in lockdown 1, about 70% in lockdown 2, and about 50% in lockdown 3. TfL bus trips are still only at 70% of pre-pandemic levels at the end of September 2021. Next slide, please. So these graphs show NOx measurements from all the reference monitors in London, both the London Air Quality Network and Air Quality England Network. They show the network mean of the daily mean NOx by site type and by location. So blue is inside the ULEZ, so that's central London, and red is outside. The graphs show how measured NOx has changed from October 2018 through to the end of April 2021. The darkness of the grey shading indicates the severity of the lockdown, and perhaps as we expect, you can see that the impact of the lockdown most clearly on the curbside graph and to a lesser extent on the roadside graph. And the reduction is greater in central London than elsewhere. Overall, the impact is dramatic. Next slide, please. But if we look closer at that initial lockdown period, apart from at curbside sites, the measured concentrations are highest on the second day of lockdown, 25th of March, as highlighted by the black circles on these graphs. And for all station types apart from curbside sites, the reduction in concentration was greater after the restrictions began to be lifted from the 10th of May than when London was under the most severe restrictions, 24th of March to the 9th of May. So we need to tease apart what's causing these differences, the lockdown or something else, like meteorology. Next slide, please. So before I tell you about the inversion technique we've developed to help answer these questions, I just wanted to say a few words about the Breathe London project, which provided the data for the analysis, which I'm going to show you. And you've heard about this a little bit already from Rod Jones this morning. The project installed 100 AQMesh sensors at sites across London to measure NOx, NO2, PM and CO2. And also 2 Google cars collected reference quality measurements at 1 second resolution, driving around London for a year. And CERC carried out high-resolution dispersion modelling, including source apportionment modelling. And the 2-year pilot project finished in November 2020, and CERC funded the extension of the static sensors to the end of April 2021 to capture what was expected at the time to be the COVID recovery period. Next slide, please. So the model we've used in this work is CERC's ADMS Urban model, which is a comprehensive system for modelling air quality in large urban areas, cities and towns. It's a practical urban air quality model which explicitly represents the full range of source types occurring in an urban area, takes account of complex urban morphology, including street canyons, and provides output of short and long-term average pollutant concentrations from street scale to urban scale. Next slide, please. These plots show how ADMS Urban modelled annual average NO2 and PM2.5 in London in 2019. These are maps that were produced for the Breathe London project. Next slide, please. So the model is able to capture the very sharpest gradients in air pollution concentration close to roads in central London. Next slide, please. So the inversion scheme we've developed uses monitoring data to adjust emissions to reduce error in the ADMS Urban model predictions. So we use ADMS Urban to generate a first guess modelled concentration at each monitor for each hour for the period of analysis, using a first guess or a priori set of emission rates. We combine that with monitored values and known background values. And the emissions, monitor data and background concentrations are all given uncertainty levels. Then the inversion scheme minimises a cost function, so it changes the emissions to improve the modelled concentrations, given the uncertainties for each component. So in essence, if something has low uncertainty, then it is costly to change it, but if the uncertainty is high, then it can be changed with little cost. Next slide, please. The result is a revised model concentration for each monitor for each hour and a revised emission rate for each source for each hour. So in this analysis, we've looked mostly at NOx, although I will show you some results for PM2.5 as well. For London, the ADMS urban modelling used metadata from Heathrow. We've used emissions and traffic flows for 2019 from the London Atmospheric Emissions Inventory, or LAEI. Upwind hourly background concentrations are from rural AURN monitoring sites outside London. And hourly modelled NOx concentrations were produced at 117 LAQN and AQE sites and 82 AQ mesh sites. There's a higher observation uncertainty of 30% than the reference monitors, which we gave 10% in this analysis. Next slide, please. So to the results. So this slide shows the NOx concentration results from the inversion scheme from January 2020 to April 2021. So the red line shows the observed value, the green is the original modelled value, and the blue is the adjusted modelled value calculated by the inversion scheme. The top panel shows the results at AQ mesh sites, and the bottom panel shows the results at reference sites. The fact that the adjusted modelled and observed values are almost the same, at least for reference sites, shows that the inversion is working. The inversion has to a large extent corrected the error in the modelled values. Remember, we attributed higher measurement uncertainty to the AQ mesh sensors, so we should expect the adjustment to be less complete at AQ mesh sites. You can see the impact of the lockdown on the 24th of March straight away. Before the 24th of March, the model needed hardly any adjustment to coincide with the measured values. A few days before the 24th of March, the green line starts to diverge from the red and blue lines, meaning that the emissions must be diverging from the emissions inventory at that point. The peak on the 25th of March can be seen in the model predictions, so it's due to weather conditions. The gap between the original models and the observed values is greatest right at the start of lockdown, and while this reduces towards the end of the period, there's still a significant difference, even in April 2021. Next slide, please. So while the previous slide was looking at across all sites, the next few slides look in detail at a few individual sites for March 2020. This shows the original hourly modelled concentration in the top panel and the adjusted levels in the bottom panel. The colours represent the modelled contribution from different source types, and the values are stacked, so the top of the coloured area is the total modelled concentration. The black line is the observed concentration, so it's the same in both panels. This particular site is an urban background reference monitor, and there are a couple of things to note. Firstly, there are some periods before lockdown where the original modelled concentration doesn't match the measured level, but the inversion adjusted modelled concentration does. Secondly, after lockdown, it's clear that the model overestimates concentrations, which the inversion fixes. Next slide, please. This site is a curbside reference monitor, and concentrations are generally much higher here than on the previous slide. The modelled concentration at this site is dominated by traffic emissions from a road right next to the monitor, represented by yellow on the graph. Here again, you can see that the inversion adjusts the model result to match the measurements, but here there's a bigger impact of COVID restrictions, and you can start to see the impact earlier, following the initial public announcement on the 16th of March. Again, the inversion fixes the emissions to correct the model. Next slide, please. Finally, this is a roadside AQ mesh sensor on a much quieter road than the previous site. You can see how dominant the traffic emissions are near to the monitor are, but also you can see the difference that the higher measurement uncertainty makes. The inversion allows small differences between the adjusted, modelled and measured results. Next slide, please. So all of these results are confirmed by scatter plots of the hourly data and the associated statistics. The large scatter in the original model in the left-hand column, so the top row are AQ mesh sites and the bottom row are the reference sites. So the original model is dramatically reduced, the scatter is dramatically reduced in the adjusted model concentrations, which are in the right-hand column, and the correlation is greatly improved. So the correlation is now close to 1 for reference sites where we prescribed lower measurement uncertainty. So the inversion scheme seems to be behaving as expected in terms of concentrations, in that it is successfully managing to adjust the model concentrations to match the measured data, subject to the uncertainties that we've input. But what does the inversion tell us about the emissions that it's produced in order to generate these adjusted modelled concentrations? Next slide, please. So this graph shows the percentage change in emissions in blue compared with pre-lockdown levels, and equivalent for concentrations, which is in red. Again, the darkness of the grey shading indicates the severity of the lockdown measures in place at the time. The emissions change is much more dramatic than the concentration change, with a reduction of about 60% in that first lockdown period compared with pre-lockdown levels. The impact on 24th of March is immediate. You can then see the emissions gradually increase during summer and early autumn 2020 as restrictions were relaxed, but they hadn't returned to normal even by the end of April 2021. In lockdown 2 in November 2020, emissions were down 30% on pre-lockdown levels, and in lockdown 3 in early 2021 they were down around 38%, according to these estimates. Next slide, please. And if I highlight the weekend days, you can see that post-lockdown, the lowest derived emissions occur at weekends, particularly during the 3 full lockdowns, which is likely to be due to the closure of retail, hospitality and entertainment venues. Next slide, please. So we've carried out a similar analysis for PM2.5 using data from 50 reference sites, but the picture is much less clear for PM2.5. Looking at the modelled and measured concentrations across all sites, it's hard to make out any impact of the lockdown, although we have seen a small impact at curbside sites where the traffic component is most significant. Background concentrations, of course, dominate total PM2.5 in most locations. Next slide, please. So, to summarise, we have developed an inversion system that combines measurements and ADMS model data by adjusting individual source emissions to optimise dispersion model results, subject to estimated uncertainty in the measurements and in the emissions. We've applied this inversion technique to assess the impact of COVID-19 lockdowns on road traffic NOx emissions across London. And we found that measured NOx concentrations in London reduced significantly following the imposition of the COVID-19 lockdown on 23rd of March, with the greatest impact, around 60%, at curbside and roadside sites in central London. And the inversion analysis has shown that the impact on road traffic NOx emissions is similar, around 60% in that first lockdown. We found that the lowest road traffic NOx emissions occur at weekends, which is consistent with the government traffic figures, and also it's likely to be due to the closure of retail, hospitality and entertainment venues. And by the end of April 2021, we estimate that road traffic NOx emissions were still around 30% lower than pre-lockdown levels from this analysis. And we found it difficult to discern any noticeable impact of the COVID-19 restrictions on PM2.5 levels generally, although these results are highly sensitive to background levels, and we did see some small effects at curbside sites, which I haven't really shown here. Next slide, please. So as I mentioned earlier, this work was funded by a NERC COVID-19 emergency grant with the University of Cambridge and ACOM, and we're very grateful to Rod Jones, Jim Mills and their teams for their assistance, as well, of course, to my CERC colleagues who've helped with this work. The areas where we're currently developing this analysis are firstly in refining the uncertainties and error covariances that we use for both the emissions and the measurements, which I've talked a little bit about the uncertainties that we've used for the observations here. I haven't gone into detail about the uncertainties that we've used for emissions, and we're really still in the process of refining exactly the levels that we should use for that. Secondly, the modelled emissions include not just road traffic, but all sources of NOx in London, for example, commercial and domestic heating sources, aviation, etc. So we're investigating the impact of successive lockdowns on those emission sources as well. And thirdly, we're applying this technique to CO2 in London using the AQ Mesh CO2 measurements that were gathered during the Breathe London pilot project. And finally, we're also applying this technique to NOx and CO2 in Glasgow ahead of COP26 in November, and using the measurements which Rod and Pete have already talked about in Glasgow. Thank you very much for listening to my presentation, and I would be happy to take any questions.